Good evening, everyone. And again, thanks to the organizer for putting together this wonderful gathering for all of us. And reflecting on yesterday's discussion about philosophy or foundation of quantum mechanics, and listening to the talks today, Misha Lukin is, if you want to say, shut up and calculate, he's doing that for sure. He's going to build the best quantum computer and going to calculate. And I hope I come from the angle that following Magdalena's point is that let's move beyond the single particles, but do measurements. Since measurement has been the foundation of quantum mechanics, let's just keep measuring. You can ask questions about philosophical debate and so on. Or let's go to the lab and keep measuring and see things where start to break down, and that's where the theory will reach its limit. So hopefully I'll give you the sense of building clock, I argue, is one of the very interesting quantum systems that you can take measurements to the extreme frontier. Perhaps one day we can even test one theory, strongly interacting many-body systems can be probed by clock, and that's the connection to the little universe we're trying to build in the lab. So that's the point I'm coming from. Let's see. So since we're talking about, as Magdalena said, moving beyond the single particle, let me start with celebrating some of the heroes who are actually on the island, and you will see many of the faces actually throughout my talk. And Dave Weinle in the late 90s was already trapping single quantum particles, and in this particular case, mercury ion, it was building single mercury ion clock, and was already surpassing, the precision was already surpassing cesium clocks. And of course, we learned in the in the 80s and the 90s, there's a tremendous progress of laser cooling of particles, and very quickly that led to the success of demonstrating a new state of matter, what Bose-Einstein condensate. And this is the 30 years anniversary of BEC, by the way. And very quickly this was followed by the demonstration of degenerate Fermi gas. What these developments, based on these incredible quantum mechanic people doing work in the laboratory, is producing this incredibly low entropy quantum systems that we can start to dream about putting into optical lattices, or now these days, of course, you can do tweezers without going through quantum gas. But then you start to dream about the possibility of building atomic clocks that can perhaps have a chance to catch up with Dave and maybe even surpass, because you can have many thousands or many millions of these particles all working in parallel, as long as you can design traps such that the trapping potential itself does not place a limit on how well you can measure the clock energy difference. So we immediately started to do this kind of work. At the turn of the century, the simplest possible lattice is this just one single dimensional lattice with a radial reflecting laser beams. You put dozens of atoms per pancake, if I may call that. And you start to turn on the clock laser. The clock laser is basically doing, this is a fictitious spin half system, and you start to rotate on the Bloch sphere. And we picked the fermionic atoms, in this particular case, strontium-87. And the reason is because they are not supposed to interact. But of course, as the clock precision progressed, we can clearly see that these fermions just have to have their wave function to be anti-symmetrized. And if the clock precision goes forward, you are starting to explore many-body quantum physics. You start to explore sort of a spin network of interacting spins with the clock to probe this. And I want to recognize key contributions who kind of laid the foundation for us to use clock to probe many-body physics, to Alexei Gorshkov, Anna Maria Ray, and Peter Zoller. And especially Anna Maria Ray and Peter Zoller have remained long-term collaborator on theory aspect of this clock work. And so one way to solve this interacting problem, if you have a single pancake, the atoms start to interact through the so-called P-wave interactions. And it's interesting to probe interacting many-body physics, but for clock, that presents a limit. And so one way to solve this problem, in fact, Magdalena cited this paper already, is to build a so-called Wannier-Stock lattice, where we start to make extremely shallow optical lattices. And I purposely exaggerated that between the pancakes, they have a gravitational potential energy difference between those. when the lattice becomes so shallow, the wave function of the particle is delocalized. In fact, the wave function spreads over several different pancakes. So you can think of each particle, in fact, is a wave function that's spread over multiple pancakes. Why this is such a useful thing? Well, as we probe the ground to the excited state with the laser wavelength is not commensurate with the spacing of the lattice, such that each pancake of those atoms are being dressed slightly differently due to the propagating laser phase. So you can think of these atoms as identical fermions interacting within one single pancake, but between neighboring pancakes, because their wave function can overlap, there's an interaction between non-identical fermions, which means they can interact with S-wave. So by controlling the lattice depth, you can sort of engineer a many-body quantum system where S-wave, T-wave on the mean field level can be canceled. And how well we can do this job? This is the in situ imaging of the atomic cloud, and along gravity is pointing to the left. And you can take an image of those, and you can see at a particular wavelength, at a particular trap depth, if you do not go to this magic trap depth, you can see the frequency shift is very much a function of the density distribution. But when you go to this particular lattice depth, about 10 E recoil energy to suspend the atoms against gravity, the density shift disappears at 10 to minus 20 level. So that was one useful trick. And this led us to start to demonstrate this very long coherence time. Here shows you put a clock in coherent superposition, the coherence time is 2 minutes. And so now it's going to be starting to think of this as an interesting quantum resource, because I can build a clock like this. I can also drive the so-called Varnier-Stock lattice sideband, which is I'm driving the wave function between one side to another side, while I'm still preparing superposition between ground and excited state. These are the actual data called a Varnier-Stock sideband. This is when I drive on the same site. The difference between these sidebands is nothing but mgh, the gravity times the height. So this tells you can build an interferometer that will allow you to measure clock, internal spin degrees of freedom, and also gravity simultaneously. And I can show you this very quick experimental protocol. I put a pi over 2 poles, you put it in the superposition, and then start to drive on this Varnier-Stock sidebands. For example, pi, so this goes down, this goes up, and then do another pi. This goes up, this comes down. And you can see these are now a superposition where spin up is sitting upstairs, spin down sitting downstairs. And you wait for 120 seconds, as for example, that's coherence time. You will be able to measure gravity, G, and the gravitational potential, which is the redshift, all at the same time. This is exactly the idea that Magdalena just talked about. And I want to say also, it's quite interesting if you think for a second, the mass, when you drive the atom into the excited state, as she also pointed out, the mass is different by h nu over c squared. The photon has the energy h nu, E over c squared is the mass. So excited state actually has different mass than the ground state. This effect usually is very, very tiny. But when the clock is getting to 10 to minus 21, you can now start to think of the reason why Rainer's picture is here is because he was the first one when I was still a young student. He told me, Jun, one day I want to measure single photon mass, and I think we are getting close, Rainer. And so, for example, you can have the spin up here, spin down there, but you can totally switch in the sequence where spin down is up and spin up is down. And you can just do the switching differential measurements, you immediately get a single photon mass coming out. What's beautiful about this is nobody doubts this equation, but what you're starting to connect general relativity, clock, gravity, and so on, all in a kind of a unified platform. And so indeed, as Magdalena also mentioned, that we can now measure the clock down to 10 to minus 20, 21, in fact, mid 10 to minus 21, and the gravitational redshift at a 100 micron scale is 10 to minus 20. So we start to be able to measure the time dilation effect over the scale of the human hair. What if you push this forward by another 2 orders of magnitude? Now remember I talked about different S-wave, P-wave interactions, which have some complicated formulas, but you don't really need to pay attention to this. It's just collective spin Hamiltonian, where on side is a P-wave interaction, off side is S-wave interaction. But there's one more term now you have to think about, which is the so-called gravitational redshift term, which every pancake is running at a different time. Because for a common observer, okay, on the stage. And so if you look at this Hamiltonian, you will say there are terms which is not commuting with the GR, there's terms which is commuting with the GR. And if you let system like this evolve, you will be able to see how many-body physics gets modified by the presence of gravity. So gravity starts to creep into quantum many-body physics in a measurable way. Of course, not today. We needed to make a clock 100 times better, or maybe 1,000 times better, and you will start to see those effects. Akin to Marcus Espelmeyer always talks about spin singlet, spin triplet oscillation back and forth due to gravity. You can see the same spirit here. And I want to just make a very quick connection that Igor and Magdalena had the foresight. Back in 2011, they already talked about, I think it was triggered by some experiments. There was some controversy of whether you are measuring redshifts or in the atom interferometer. And so they came up with this testable proposal, which is if you split your matter wave function, but you also have a clock actually running in each pathway, and this clock will tell you redshifts, and so will tell you which pathway you actually went. Then they claim the fringe contrast will start to come down and will oscillate. And then in some sense, this is the right framework, and I want to say this is nothing but the interferometer of a non-local mass superposition, because what is the clock is, in fact, is a superposition of ground state, excited state has different mass under gravity. And so this concept has now been generalized to a more exciting frontier, the work of Peter Zoller and his student, Charles Fromental. It's a French name. I hope I'm pronouncing it correctly. And Igor and his student, actually Michel Lukin's student, they also had a similar idea of using quantum network. You can think of quantum network now allow you to connect, for example, in one particular node of a location of A, you create a superposition of many particle states, and you create a superposition. When you create a superposition with a clock drive, you're creating a superposition of a mass. But at the same time, if you can have an entanglement protocol to exchange spins back and forth between node A and node B between different locations, then you're creating a non-local mass superposition. And you can just bring back to the Ramsey spectroscopy, you will be able to see those kind of gravitational effects on using clock network. What's beautiful about clock network is then the distance can be really far. So the clock precision will be relaxed. You will start to see those effects. This is just the gravity of the Earth doing something to quantum system. If it's not quantum gravity, to me as experimentalist, it'd be super exciting to see those things. Because the quantum gravity will come if you can do these experiments. But the system is not ready, so we need to scale. And one way to scale is to look at the noise. The other way is to look at the particle number, which is also noise. Because if you look at the superposition, of course, this is exactly what Heisenberg told us. When you have two eigenstates in superposition, there's energy that's multiplied by time. This time is what we want to measure, but when we try to project the population, we have this uncertainty of the so-called quantum projection noise comes to the Heisenberg uncertainty principle. And so in order for this noise to go down, we tend to build large quantum systems so that the square root of n, the particle number, will go down. But of course, we learned from many pioneers, and including the pioneers here sitting in the audience, who told us about entanglement. These pioneers worked on photon entanglement, but we can now translate those concepts and technologies into atom entanglement, and along with a lot of people who have worked in this field. But now we can start to think about, could we inject spin entanglement into the state-of-the-art clocks and interferometers and so on, and actually show this matter instead of, yes, I can generate entanglement, but they do not survive for a long time. So this is the important point to try to see what kind of entanglement, what gain can we have when we have entanglement in the clocks. So that's the basic idea, and we use cavity QED to realize this idea. We made this lattice to be sort of like elevator. You can put atoms in sample A, move in between the two highly reflecting mirrors. It's a cavity QED effect. And then you can learn from textbook examples of Serge Karosh and Vladan Vuletic, who have been teaching us. You can use cavity QED to do collective measurements. In Serge's case, of course, it's a single atom, and nevertheless, you can do cavity QED-based so-called quantum non-demolition measurements. And so in this particular case, we can spin entangle all the atoms in sample A, and then we move sample A out of there and then move sample B. And so the operation akin to, you have this classical spin noise, classical spin coherent state, and you do this QND, which is kind of like a spy measuring the population in the ground state. You essentially achieve the spin squeezing. And then you rotate the spin squeezed state by 90 degrees and do a clock evolution. And because it's a noise that has been squeezed, you have a better sensitivity to measure this little angle, which is your time. And so last year, we were able to now reach mid parts of 10 to the 17 for clock. There you can see the spin squeezing is actually helping. But the field is moving fast. A year later, now we can actually demonstrate spin squeezing at the level of 1 times 10 minus 18. And it's 3 dB below the standard quantum limit. So it's time will tell whether we can truly like taking on LIGO type of a spirit, where we go to 10 minus 22 and so on, when we are running out of space for atoms, because I don't have enough laser powers, that we can have spin entanglement to help us to push the envelope further. And another idea is, for example, in the future, we could even imagine, generalize this two-mirror Fabry-Pro cavity into a bow-tie cavity where the sample A and the sample B itself is entangled, but between them are also entangled, and you can have the separation fairly large. This almost has the idea of this quantum entanglement network. So you can start to test this gravity on quantum entanglement and clock precision. Another way to scale up the atom number is just to build, as Misha showed us today, you can have in tweezer now, it's truly exciting, continuous atom source, potentially have tens of thousands or hundreds of thousands of atoms. We have been working on three-dimensional Fermi degenerate gas, degenerate Fermi gas of strontium atoms, put it in a three-dimensional optical lattice. We were thinking about building 1 million atoms in there with a coherence time of 2 minutes. Now we finally can demonstrate this. Not quite yet in 3D. And this will allow you to build a clock at a second. Even just 1 second averaging time will be few parts 10 to the minus 20. We're inching towards this kind of a system. But in the meanwhile, this has actually become a really interesting quantum many-body system, very strongly interacting. Very strongly interacting is only in the perspective of the person who's doing the measurement. Because the coherence time is really long, even if these atoms are interacting with micro dipoles, but we got millions of them, it's a very strongly interacting system. And that could limit the measurement precision. So we have been having fun to kind of looking at a quantum simulation of this classic Fermi-Hubbard model in 3D and how that looks into our clock system to explore SU symmetries, look at the spin orbital dynamics, spin exchange interactions, and the collective dipole couplings, the so-called Lamb shift. This is almost like a classic case of the Dickey superradiance model, except we are not looking at the superradiance, we're looking at collective dipole-dipole interactions. So it's actually a super rich physics playground. So you can speculate, since we are in Helgoland 2025, who was that? Ike Chung was speculating, so I feel like I can speculate here. What if we, there's several curves here. This is if you follow the 1970, 1980 technology of microwave, and if you want to scale this down to 10 to minus 44 quantum gravity, who talks about quantum gravity? Well, there are crazy people in this audience, including Marcus. Marcus Espomeyer has been talking about this, and we heard it from Magdalena, and actually Igor and Misha is starting to, Igor has been thinking about this, of course, for a long time. But for me, this is all new territory. But if you look at the microwave technology, will never get us there. If you follow the optical, this is the new cold atom-based microwave technology, that will still not get us there. Maybe 1,000 years from today, we can see quantum gravity. But if you follow the trajectory of optical technology, optical clocks, maybe 100 years from now, I'll see quantum gravity. But this is too optimistic because the last few years, you can say there's a little bit of a slowdown. And so if you take that curve, that's 200 years. So this is just telling you, well, maybe the technology needs another revolution. Maybe we should bend the corner, just like a microwave to optical clock. No, if bend the corner a little bit here, it may have a big consequence in many years down the road. Maybe we need another bending here. Okay, what is that another bending? Before I talk about another bending, it's fun to talk about quantum gravity because we just follow one. If you imagine you have two atoms, place yourself in coherent superposition. Now, the gravity in the excited state, the mass is different between the excited state and ground state. So imagine these two atoms are sourcing gravitational attraction between each other, but it's fluctuating because you're in the spin degrees of freedom. And that means the red shift of this atom feels from this atom in superposition would it be proportional to nothing but the excited state has the extra mass of h nu over c squared. So this is a red shift due to the atom in the excited state on the next atom. If they are fluctuating, what you will see is that if I suppose I take my quantum gas density of 10 to the 13 per centimeter cube, and this would translate into 10 to the 19 atoms. Suppose I have a laser beam that's this big, 1 meter, and I should be able to start to probe delta nu over 10 to minus 44, and this is many, many decades from where we are. So the technology that if one can, for example, put the two atoms near Schwarzschild radius, then you will see actually delta nu over nu equals to half. That's the quantum gravity. It's a kind of really interesting. You can see the scale that works out. You're a clockmaker. You just always think about what clock rates are going to ticking at different rates when you have this superposition of gravity. So these are pipe dream, completely pipe dream, but it motivates you to maybe we think about new technology. And so let's think about another scaling, right? We have been learning from mass power spectroscopy in the 50s and the 60s, and in many ways, the atomic physics community has learned a lot from these condensed matter, early pioneering work, where whether it's Dave Wineland or optical lattice work, we always relying on the fact that when you do absorption, there's no recoil, and the system is well confined, and there's a collectiveness. The only difference, atomic clock is of course using coherent light source, while mass power spectroscopy is incoherent. But if we can turn this from incoherent to coherent, while we can enjoy an Avogadro's number of quantum absorbers, you can actually do this with a crystal because these are nuclear transitions, not sensitive to electronics. And this might be possibility for scaling, And so indeed, there is such example. Thorium-229 is one very famous example that's been, has a lifetime of, in this plot, and we can now experimentally measure 20 minutes. But energy scale is on the scale of 10 eV, which is within the reach of optical technology. And Edgar Pike initially proposed to build this following some earlier work in Soviet Union, in Russia. I think Edgar Pike and Christian Tam of PTB first made a proposal how to turn this into a clock. And in fact, last year, they were able to see the transition that being laser excited with their full-wave mixing laser about 20 gigahertz line width. We don't see structures there because the laser is very broad, so we need a high-power narrow line width laser. And I want to tell you that story a little bit. We have the visible light, we have the XUV, VUV light. In the visible light, we're doing a pretty good job to be able to move clock forward. You have to build very stable lasers. This was actually a very long 18-year collaboration between our lab and the PTB in Germany, and allow us to build this cryogenic silicon cavity that has now going down to just a few millihertz line width on the laser. Through the work of a frequency comb, such an optical phase stability can be transferred basically anywhere in the visible, and that problem is solved. The problem is on the in the extreme ultraviolet or vacuum ultraviolet region, there's only really free electron lasers and synchrotron radiation to do this physics, and they don't have the spectral resolution power. But we also know from attosecond pioneers that you can generate tabletop extreme ultraviolet radiations if you have a big enough laser field, with an electrical field reaching 10 to the 13 watts per centimeter square and so on. You can actually ionize an atom. The electron will coming out of the Coulomb potential, gets snapped back in during this so-called recombination process, generating many, many harmonics, odd harmonics. And of course, that doesn't have a spectral resolution either, because each harmonic contains the line width of the entire visible spectrum. These are for femtosecond lasers. But you realize if you can just keep doing this experiment, if the process is coherent, if you're generating this pulse every 10 nanosecond, and if there is a phase coherence between these attosecond pulses, there's a possibility to have interference and actually have a frequency comb in extreme ultraviolet. It's just technologically, it's pretty hard because you're talking about 10 to the 13 watts per centimeter square for one pulse, and you have to do it again every 10 nanosecond. So this huge power have to be built up. And the way that we solved this problem is by, we've actually been working on this for 20 years or so, is by injecting these frequency combs into a Fabry-Perot cavity, and so you match up the free spectral range with the repetition frequency so that every single comb is mode matched into the optical cavity, and every one of them gets built up. And if that's the case, you do not have to sacrifice the repetition rate. Inside of the built-up cavity, you have a huge power of this ultra-fast laser. And so we were able to, back in 2005, we were able to generate about a picowatt of a VOV frequency comb. And after 20 years, we can now move from picowatts to a milliwatt. And that's enough to drive the nuclear transition, thanks to Thorsten Schum of Technical University of Vienna, who provided us with the thorium-229 doped crystal, doped in calcium fluorides. And the concentration is 4 times 10 to the 18 per cc. And this is the crystal when we first received it. Now, here's the power of the frequency comb. You have an unknown transition somewhere. But with a frequency comb, as long as you know the transition is within this bandwidth, you scan the comb, and every transition is going to show up. And indeed, as soon as we do this, you get a surprise. Well, it turns out it's not a surprise because nucleus are sitting inside a solid state material, has an electrical field gradient, acting on this liquid droplet model of a nucleus have an angular momentum between the ground and excited state, and they have a nuclear quadrupole moment, which will interact with the electrical field gradient and will split the line. So we can measure all these now with high precision. In fact, this measurement immediately led to Mariana Safronova to convert from the ratio of the quadrupole moment to the ratio of the volume of the nucleus. So when you excited the nuclei from ground state to the excited state, you find this little soup goes a little bigger, and the volume changes to 550 parts per million. So from this, Mariana figured, in nucleus, the binding energy has both Coulomb interaction and a strong force. And even though we are measuring only 8 eV worth of energy, but it's actually sitting because of the volume difference she can calculate. We're actually changing the Coulomb interaction energy by 50 keV. So if something like dark matter is coming, and there's one postulate anyway that allows you to change the fundamental constants of alpha, this fine structure constant alpha would have been amplified. Its impact would have been amplified by the ratio of this energy shoulder sitting on top of this energy transition that you're actually measuring. And so this would be a really handy enhancement of a factor of 6,000 if you want to use nuclear clock to search for dark matter when using atomic clock, which is much less sensitive as a reference point. So to do that, we need to connect optical atomic clock with nuclear clock. And fortunately, as I mentioned, it's already trivially done because this frequency comb conversion is completely coherent. So this frequency comb that's driving the strontium transition is used to drive the nuclear transition, and the frequency ratio immediately is 12 13 digits, and it's coherently connected. We used this little symbol to indicate yin and yang, atomic and nuclear clocks. So just to conclude, Thorsten has given us now more crystals grown at a different time with different concentration. We want to understand where the line width is coming from. we haven't reached the promised line width, which if for 20 minutes coherence time, 20 minutes lifetime, the coherence would, like a strontium, the coherence should be incredible. The line width should be on the order of tens of microhertz. And we are far from that. We had, when we first saw the transition was on the order of 300 kilohertz, but we can now move down to 20 kilohertz. But more importantly also, to probe, after all, this is inside the crystal, and I want to probe some basic parameter. For example, if I change the temperature by 150 Kelvin, what does the frequency move look like among 3 different crystals? To our pleasure, the 3 crystals actually agree with each other quite well. And in fact, there's a 0 turning point at this particular temperature of 195 Kelvin. The crystal frequency does no longer depends on temperature. So we thought, excuse me, we thought we will plot this kind of fitted this out and look at the residual frequency. But more impressive is just looking at the 2 lower doped crystals, C13 and C10. And you can see over the past 3 or 4 months measurements, they agree within a few hundred hertz. And I hope this is the very beginning to show how stable a nuclear clock can be. We hope this will be a system that you will bring on an airplane and go to a different continent and it will still be the same frequency. It's a truly integrable system that you can build nanophotonics around it. So with that, I want to end my talk kind of reflecting on the fundamental physics. We learned from mass power spectroscopy, in fact, is where we learned redshift first, right? In this historical experiment by Pound and replica in Harvard, they were able to show, you put emitter in the basement and you see absorber on top of the Harvard building. I think that's actually Lyman Laboratory building. And it was a frequency, actually, if you just convert this, it's a 20 meter difference. That's about 2 times 10 minus 15 level. They were able to see the photon. They call the red shift because they think the photon has changed the energy. Of course, it depends on the transformation of a coordinate. And of course, we now know with 10 to minus 20 level of precision, we can measure the red shift over 100 micron or so. And it's interesting now we have nuclear clock and atomic clock at the same time. So I think it's going to open up some games. I hope the dream is not completely bogus. 100 years from now, we might be able to use a clock to probe quantum gravity. With that, I want to thank many amazing students on the strontium atomic clock, many long-term collaborators. I want to acknowledge their contribution. And also for nuclear clock, actually this one singular graduate student spent 7 years in the lab, and in his last half year saw the nuclear transition and did all the measurements. Thank you very much.
Thank you very much. So there's still time for 2 or 3 questions, if there are any. Well, actually, you should probably better go to the mic, yes, otherwise we don't hear you. Good?
Yeah, I wanted to ask about this weight of the photon in the following. So, as you mentioned, one can directly think of observation of redshift experiments as a confirmation of the mass energy equivalence as it enters the Hamiltonian of the atom.
Yes.
But the fact that the energy levels of the atom change its mass is because the photon absorbs. So I wonder why can't one interpret the redshift experiments that are done in your lab, and they were already done by Dave Wineland, as measuring the weight of a photon that is trapped in the excited state of the atom?
Yeah, thank you. And it turns out, if you take the mass defect as your Hamiltonian, it built into your single particle, single atom Hamiltonian under gravity, and you absorb a photon, indeed the mass changes due to the h nu over c square, because the photon carries energy. But if you expand it, now you have a ground state and excited state have a different mass. If you expand it out under gravity, the redshift and the second order Doppler and the gravitational motional time dilation and the gravitational time dilation both come out of this single particle Hamiltonian. So start to think of them as being equivalent. And in fact, measuring a single photon mass, in principle, is not that interesting. But if you start to use the single photon mass as a handle to see decoherence and so on, like you proposed, and I think it's just a way to rethink, in your original proposal with the Eagle, you were thinking about, if I can keep track of a proper time, I would know where the frequency shift is. Now this can be expanded to think of, it's just nothing but non-local superposition of mass distribution. It's the mass, if you talk to Marcus, his mass is a nanomechanical oscillator. Here the mass is just spin, but the spin carries the mass because of the mass defect.
Okay. Maybe, of course, I'm a big fan of what you're doing and really admire the precision that you achieve. And then you have this very bold vision to go in 200 or 2,000 years to a very low limit. And so I was just wondering, so of course you have to scale up things, you have to have more atoms, you have to expand your beams, and then you will start to also average over electric fields, magnetic fields, the blackbody radiation will be different in different places.
Yes.
So did you try to make an estimate how hard it will be for an experimentalist, even a very ambitious experimentalist?
Yeah, that's why I think in the plot that was audacious enough to show, I remember I didn't talk about this, but most of the time, John Presco's here, he talks about NIST. I'm not going to talk about NIST, but I'm talking about noisy coupling to environment. There will be a lot of things along the way that you have to study the opportunities of couplings, electromagnetic field interference. If we want to do gravity, electromagnetic field is going to be the big roadblock. And so we will have to understand all that kind of noisy couplings. And it's an opportunity to really push the envelope of understanding strongly interacting many-body physics, from one stop.
And then the precision that you've shown is stunning already. And the question is, how will this transform also in accuracy?
The accuracy right now is limited by black body radiation. So if you want to compare clocks, then you clearly have to control their temperature, unless you cool them down. But you can cool them down. So black body in some ways is a single particle effect, and it's technically it's relatively easy to achieve. But of course, precision does not guarantee accuracy. Precision is a necessary condition for accuracy. It's not a sufficient. So you need to, at the same time, if you want to be the clock as a timekeeper, accuracy is really important. If you say, my clock is just also doing fundamental physics, then in principle, you can do differential measurements and so on, even if they have common black body shift. That wouldn't prevent you from seeing quantum gravity.
Okay, good. I think there's another question.
Yeah, thanks for the great talk. I didn't catch why the line width of the thorium nuclear transition was so different. Then you said it's 200 kilohertz instead.
Yeah, and now it's
why can you control it?
Let me see if I actually have a slide. The reason is because in this, we think this is something. Yeah, so I have a slide here. So it turns out, as you can see, this is actually the line width as a function of the doping. What we think that's happening is when you dope, the doping, the crystal itself is a calcium fluoride, and you're doping with thorium. And when thorium comes in, it kicks calcium out, creating the so-called microstrain effect. And I even have this picture. Yeah, and so the microstrain creates the varying electric field gradient. And so if you have a different sites like this, then in principle now you have an inhomogeneous broadening. So it's like you have an electric field gradient that's spread out. What we want to do is multiple fold. One is these kind of effects people have, well, not in nuclear clock kind of a context, but in NV centers and so on. If you have sufficient laser power, you should be able to do pulse manipulation. And this is something we are already working on in polar molecules and so on. You do flow K engineering, you can remove lots of these dephasing effects. The second, you can also talk very sweet with Thorsten and ask him to grow, instead of a calcium fluoride, thorium fluoride. what if you have a thorium-232 fluoride crystal and you dope it with thorium-229, then chemically the doping did not affect the crystal structure, and the Thorsten is already on that path. So hopefully, you know, with the new crystal, this language will be a lot narrower. But that's something, again, a lot of physics to be learned in material science side, with a nuclear clock as a probe.
Okay. So actually, since we're a little bit over time, I would like to thank Jun once more and all the speakers of this session.